me out to the ball game. Take me out with the crowd.
It's a fun job. I feel lucky to have fallen into this line of work, and I couldn't think of anything better than to go to work and build cannons and shoot things at high speed.
I was 13. I had just turned 13, if it was the early summer of 1944, and I think it was. My dad, during this year, 1944, was head basketball coach at Washington State. And because of the war and Buck Bailey's absence, he was also baseball coach. With so many males off at war, my dad worked in the WSU foundry. And they were working on an aluminum bat. We used it playing ball. It would make a funny boink noise that wouldn't be funny anymore because they all used metal bats. I have no idea what happened to the program. I know we weren't asked to give that back, and there were others.
In the 70s, they started making these aluminum bats. Why did they take off in the 70s and not in the 40s? I don't know the answer, but I have a guess. The aluminum that they use for bats today is a high-strength aluminum, and it's made from aluminum tube. And I don't think they could get the strength properties out of a cast aluminum bat that they can out of the aluminum tube. So I'm guessing the reason this bat didn't take off may have been that once you got a stronger player hitting the bat, that they didn't hold up as well. Our lab is primarily associated with softball. We do most of our work for the ASA, which is the Amateur Softball Association. One thing we do is we certify bats for ASA. We also certify bats for the NCAA, for baseball. Each of these associations has come up with a standardized test. We actually help them develop the test so that what we measure in the laboratory has some relevance to what occurs out in play. We also test balls. We talk about the bat as being so important. It turns out the ball is an integral part of what happens with the bat. If you look at a bat and a ball collide, the barrel of the bat is going to deform roughly about 1/8 of an inch. The bat is metal, and metal is very elastic. So that 1/8 of an inch that comes in, it's just like a spring, and it's going to just give that energy right back out. But for the ball, as it comes in and deforms almost an inch, much of that energy is dissipated. So here's a golf ball. Golf balls are very elastic. They have a coefficient of restitution, we call it, that's almost 1. If it was 1, it would bounce up back to my hand. But if you do that with the baseball, it loses most of its energy upon impact. When a person is designing a bat, if they can come up with a way that the ball deforms less, then the ball will lose less energy, and it will go farther, it will be hit faster. It's hard to say what's going to happen in the future. I've been amazed by the things that have come up so far. People are working with nanomaterials, and some people are actually coming up with two-piece bats, kind of like a fishing pole. We talk about aluminum bats being developed in the 40s and first proposed in the 20s, and it wasn't until the 70s that they really took off. We may see some of this as well with composites, for instance. People were messing around with composites back in the 90s, but it wasn't until after 2000 that people figured out how to make a composite bat that would hold up and be durable, and then they just took off with the storm. So some of these other technologies may be like that.
Or it's 1, 2, yeah,